All right, good afternoon. Today's lecture is 2020-10-12, and this recording is for the Math 100 asynchronous class for today. This class will be, brief. We'll get through pre-algebra. We'll talk about linear equations, and that'll save physical therapy math for our physical class, or not physical, our class together on Wednesday. So when we last left, we were talking about solving equations and how to solve general pre-algebra equations. Again, we're not going to have a ton of complicated questions in this class. The class is to teach you the basics of doing basic pre-algebra so that you're prepared to do things in the clinic. So I have a couple examples here after we've gone through this. We talked about variables, right? And that variables are nothing more than solving for an unknown. There's not a big mystery behind it. They can be any letter you want. If you don't like X, pick a different letter. But what they do is they allow us to put a quantity in there for something we don't fully have the information on, right? The last one we have is the one I had brought up here, which was the 3 minus x question. But there are a number of different ways. We cannot solve a variable question unless we have the equal sign. If we don't have that equal sign, the only thing we can do is evaluate it, right? We talked about that briefly. Whereas if my question, instead of having that 3 minus x divided by 14 equals 14, where if we had something where it was just instead just 3 minus x, and then I said to evaluate where x equals 1, right? At that point, you're not solving. You're just evaluating for what that statement says. The other is an equation, which is what we have down there on this first area. This is a full-on equation because we have an equal sign. We could also have, in more advanced math, we could have something like greater than, less than, equal to, stuff like that. But that's going way beyond what you guys need for this class. So don't totally freak out. So let's look at an example problem here. So a clinic order supplies for the month. The gloves cost $324. Masks cost $37. Alcohol swabs cost $22. The total supply order is $400. How much is the paper towels cost that we're missing on the invoice? This happens sometimes. It may happen on a bill that you have or something of that effect. What we're looking at is solving for an unknown. We don't know how much paper towels cost. So wait, why is our bill $400 when everything else, only comes at $383? Well, then we got to solve for the unknown. You would normally just say, well, how much plus 383 equals 400? Well, that's exactly what doing algebra is. We're just, instead of saying what does that, is just putting an X in place of that. So as you look down at the bottom, we're going to put all of our numbers together, right? So our gloves plus our masks plus our alcohol swabs plus our paper towels are going to equal that $400. We're going to put the X in for the paper towels. So we have 324 plus 37 plus 22 equals, or plus X equals 400. So if we add all our numbers up, 324 plus 37 plus 22 is going to equal 383. So our basic problem in reality is 383 plus X equals 400. And then what we're going to do in order to solve this problem, right, is we're truly going to subtract 383 from both sides, right? That's going to eliminate that over there. And remember, whatever we do to the left, we do to the right. Whatever we do to the right, we do to the left. So that's going to leave us 17 on the right. So X in that case is going to equal 17. So your clinic, here we got a patient that drinks 472 milliliters of coffee, 900 milliliters of water, 200 milliliters of Coke Zero, and 20 milliliters of cough syrup. Patient urinates out 1,152 milliliters of fluid. If the input and the output are to be equal, how much would the patient have to vomit? So basically what we're saying is, if all things are equal here, and this is not 100%, true to patients, because things aren't always going to be 100% equal with the body. Excuse me. Because you're going to retain fluids and stuff like that. So it's saying, if my intake equals my output, how much did I throw up? Yay, right? Or the technicolor yawn, or whatever you want to call it. So we're going to put our total that we're intaking over here to total that we're outputting over here. So our total that we're inputting is the 472, 900, 200, and 20, right? The total that we're outputting is our 1152 plus an unknown quantity of vomit, which is going to be our X. So we're going to solve it down, right? And the easiest thing we do at this point is subtract both sides. Take 1152 out of both sides. That gets rid of that there, right? And then here we got it on that side. So then we just do a simple addition. Add all this up, subtract that from it. And the patient threw up about 400 milliliters of vomit, 440. So these questions aren't that difficult. Let's look at one more just so that we can kind of do one together. So let's look at a problem where we have an x in the denominator. So let's say 220 times 3 over x equals 9. All right. So this is a little more complicated because we got x in the denominator here. So the first thing we have to do is get rid of that x in the denominator. How do we do that? Well, if we multiply both sides times x, we're basically multiplying both sides times x over 1. X over 1. And we know that if we do this, that cancels those out. And what we'll end up with then is 220. Oh no, I can't write 220 today. Times 3 equals 9x. All right, so I'm going to move this up here real quick because I ran out of space at the bottom of my sheet. So 220 times 3 equals 9x. And you'll see why I didn't step this out. I can just multiply this 220 times 3 and get my 660, which is possible. But you'll see why I didn't do that right now. Next thing I need to do is divide both sides by 9, right? So divide both sides by 9. Well, if I do that, I can simplify this a bit and get rid of that 3 and make that 3, because those will cancel each other out slightly. Then all I have is 220 divided by 3 equals x. So in that case, then all I have to do is divide the 220 by the 3, right? So get out your little handy calculator, divide 220 by 3, and it's going to be about 73 1/3, or 73.3 repeating. That's it. That's as hard as math problems are going to get, honestly. I'm not going to go into x squared plus 9x plus 7 equals blah, where you might get 2 answers for x, where x could equal 1 or x could equal 3. Excuse me. We're not going to do that. All right, so let's clear my annotations here. I hope that makes sense to you for this part of it. I think that's my last example here. So let me bring up the next PowerPoint, which is linear equations and graphs. So this is where I usually start losing people, but we're going to make this as simple as possible too. So we're going to new share it, linear equations and graphs. All right, so you all should be able to see linear equations and graphs now. So when we're looking at this, we're going to talk about the coordinate plane, we're going to talk about linear equations, and we're going to talk about graphs. So what is the coordinate plane? Well, the coordinate plane is this fun thing that we used to have, though. We used to have to draw on graph paper, right? Where going up and going right is positive, and going left and going down is negative. So it gives us an x-axis, a y-axis, an origin, and quadrants. So there's our beautiful x-axis. There's our beautiful y-axis. X is horizontal, y is vertical. And why is y vertical? Because. Then we always start at this origin. Origin is nothing in the x, nothing in the y, or 0, 0. Our quadrant 1 is our pure positive quadrant, meaning that both x and y values are positive. And then we just go counterclockwise. Quadrant 2, quadrant 3, and then finally quadrant 4. So this kind of explains it. In quadrant 1, both x and y values are positive. In quadrant 2, x values are always negative, y values are always positive. Quadrant 3 is our double negative, right? X and y are both negative. And in quadrant 4, x values are positive and y values are negative. when you're mapping a point with the setup of x comma y, you would use the x coordinate to move along the x-axis, either positive or negative, and then the y coordinate to move on the same axis. Why is this important? Well, linear equations, right? So linear equation is an equation where the graph of said line or said equation forms a line. Therefore, linear equation of a line. The equation is said to be linear when a constant change in x produces a constant change in y, right? That's also known as the slope. We'll talk about that in a bit. Collinear points are points that exist on the same line, right? So they're points that go along. The slope is the measure of the steepness of the line or the rate of change listed in the rise over run, right? Similar to what we're going to talk about with wheelchair ramps. In linear equations, all variables are to the first power, right? So we have 3x plus 12y equals 11. That would be a linear equation. X squared plus 13x plus 4 or minus 14 equals 3 is not, because x squared is not raised to the first power. The first thing you need to do when you're looking at making a graph is you need to create a grid determining, the line values themselves. So here we have a linear equation that says x plus y equals 1. What does this mean? Well, so what we're going to start doing is plugging in values for x and figuring out what values we get for y. Or we could do the reverse. We could plug in y values and see what we get for x. So in the first case here, we have x equals minus 2. So therefore, y equals 3. Well, why is that? Well, if we plug that in, so minus 2 plus y equals 1. In order to clear this out, we're going to add 2 to both sides. So we have y on the side alone over here, y equals 3. And that's basically the way you're going to solve linear equations. You're going to go down and plug a value in for x and get a value for y. Plug a value for y. Excuse me. Get a value for x. Whenever you're looking at these equations, if you ever are questioning if you've got the right numbers, reverse it. So if you check based upon x, put the y in and see if you get the same value for x, right? So let's see. So we had that x plus y equals 1, right? And we said that we got 3 for y. Well, let's plug that in. So x plus 3 equals 1. Well, how do we get rid of that? We got to subtract 3 from both sides. So then x would equal minus 2. All right, we got that one right. Yay. What this gives us is consistent points we can actually plot on that graph in order to make a nice line. So now we can go over to our graph here. Boom. So we've got some points. There's our graph. So when x equals 1, y equals 0. When x equals 2, y equals -1. And it just keeps moving along. That allows us to give us this nice line that runs through it, right? So in this case, we'd have a nice line. And remember that a line itself, let's follow this up here, goes on into infinity and beyond, right? There isn't a start or an end point for that line. It keeps going on to infinity. As long as we have values, we'll have a response, right? All right. So now that we've plotted our data points, we can now draw a simple line through those data points to give us our visual representation, which is what I just did, right? Where's my coordinate plane? Boom, look at that. We got that beautiful line going on. So no matter what we do, we can then even figure that out by going back and looking and going, okay, well, what if x is 10? Well, if x is 10, y is -9, right? So when you look at this, every time x goes up by 1 point, y goes down by 1 point, right? So here we have x is 0, right? At the point that x is 0, y is 1. We change that. Now x is at the 1 position. Well, y is now 0. X is at the 2 position. Y is now -1. So that's how we're looking at the slope, or the way that the line inclines, right? So the rate of change can also refer to as the pitch or grade of a line. Again, much like the grading of hills on roadways. The slope is symbolized by the Greek letter delta, which is delta is the math sign and science sign for change in, right? So when you see that delta, that's the one time you can expect change. Get it? Ah, ha, 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 ha. Right? So when we look at this, the rise and the run is the change in y coordinates over the change in x coordinates. So it's saying here, y1 minus y, or y2 minus y1 equals x2 minus x1. That gives us our slope. So let's look at our previous example here, right? We have our numbers, x plus y equals 1. If we plug in that slope formula, right, we'd ascertain something like this. For every time that y goes up by 1, this is what this is saying, right here. So we plugged in 2 different y points, boom and boom. And we then turned in and plugged in 2 different x points, boom and boom, boom and boom. When we did that, we find out that for every positive change of 1 in y, we get a negative change of 1 in x. Well, we'd also know that is the opposite as well, because basically what that's saying is 1 over 1 negative. Doesn't matter where you put that negative sign at that point, as long as it's on one of those two. So that's saying if x changes by 1, or if y changes by 1, which is our top number, x is going to change by -1. It would also be the same as saying if y changes by -1, x changes by 1, because again, that where you put that minus sign is not truly academic at that point. So every positive change of 1 on the y value, the x value will change by -1. The converse would also be true, which is what I'm trying to get at. For every negative change of 1 on the y value, the x value will change by +1. And that's how we get that beautiful slope going. When we're looking at this, we have a couple of things that we do use that slope formula for, is finding out the x-intercept and the y-intercept. The x-intercept is the x-coordinate where the line crosses the x-axis, where y, the vertical value, is 0. The y-intercept is the coordinate value where the line crosses over the y value axis, where again, x is equal to 0. So that gives us this fun slope formula value of a line. A linear equation is written in the form of y equals mx plus b. And why do we have this fancy formula? Well, it helps us look at and draw a line easier. We can do the same thing we just did. We can convert this y equals mx plus b into a standard form, right? Which was that ax plus by equals c, where a, b, and c are real numbers and are both not equal to 0, right? So where a and b are not equal to 0, because if we have 0x, we only have y. We don't have we just have a straight vertical line at that point, right? So y equals mx plus b is kind of our formula there. So let's look at x plus y equals 1, which is our previous formula, right? That's already in our standard format. We know that our x-intercept is 1. We know our y-intercept is 1, right? If the y value is set to 0, the x-intercept is 1. If the x value is set to 0, then the y-intercept is 1. And we can look at that by going back to our beautiful formula back here. Here we are, right? So the x-intercept would be the area where the line crosses the x-axis. The y-intercept is the area where the line crosses the y-axis. The slope intercept formula is line y equals mx plus b, where m represents the slope of the line, right? And b represents the y-intercept. We know that the slope is -1. We figured that out already. We know the y-intercept is 1. So therefore, y equals -1x plus 1. Right? Wait, Mr. Here, that seems a little complicated. Well, if we just look up here, x plus y equals 1. All we did was subtract both sides by a -x. And that's how we got the slope intercept formula. The standard formula line is the original setup, which is this one up here. We've already done that. That is the standard setup, right? That has basically saying 1x plus 1y equals 1. That's as complicated as these formula or the linear equations are going to get for this class, right? A horizontal line would be one where y equals any real number with no specific definition for x. In this case, x can be any value and there is no slope. So for example, y equals 4 is a horizontal line through the y value of 4, but literally can be anything on the x value, right? Vertical line would be one where x equals any real number with no specific definition for y. In this case, y can be any number and there's no slope of a line. In this case, x equals 4. It's a horizontal line through the x value of 4, but literally can be any value. What that's saying, let me go back here real quick before we end this lecture. So if I have something where, let's say my y equals 4, right? Well, if y equals 4, 4 is here, right? That would then just be a horizontal line running all the way across there. If instead we had a formula that was x equals 4, well, that would be here. And then our line would look something like this, right? If we were taking this a step further and we're not going totally into this, and we had two lines like this, and we could be looking for something, and again, it maybe if you start taking more advanced math class, you may be looking something for like this. Where do those two lines intercept each other? Or where are they perpendicular to each other? Or where do they intercept, right? Well, in this case, the intercept is going to be 4, 4. But what about where does this vertical line intercept this one? Well, we've got an intercept there. Where does this vertical line or horizontal line intercept this? We've got that intercept there. That's when we're looking for intercepts of line. We're not looking for that for this class, but there are all kinds of things we can actually do with this. Well, why does this happen? Well, we may be doing this when we're looking at creating ramps for patients. And that's the main thing that you're going to take away from this lesson, because let me go back to I want to get a blank screen here real quick. So I got my whiteboard up here. Actually, let's just stop sharing for a second. So that I've got everything up. Let me clear off my screen here real quick. Why is this important? Well, we have to know this because we will be calculating out the creation of ramps for patients. So remember, we talked about that slope. Well, how does that play into effect? Well, we talked slope is rise over run. And for a patient to get in their house, if we are creating them a wheelchair, and we don't necessarily build it, we do have to kind of sometimes develop the specs for them to build it. There's a specific ADA requirement that says if you have a ramp going up into a patient's house, let's not draw with a crooked line. That looks really bad. I don't know what that was, but that was not a line. Erase. I want the eraser, please. Why am I not getting the eraser? Anyway, so let's get a straight line here. That's not a straight line either. Can I please clear? Why does it not let me have a straight line? Your screen sharing is possible. I want to screen share. What the heck? Stop share. There we go. Screen share, whiteboard. All right, now I'm screen sharing. Okay, it was just being screwy. So here's our ramp for our patient, right? So we talked previously about rise over run. Well, this is important because let's just say that our patient has stairs to get in their house. Boom, 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 boom. Well, they need a ramp necessarily to get up those stairs to that wheelchair. It's really hard to roll a wheelchair upstairs. We'll talk about how to do that, but it's just definitely not a fun thing. Well, the ADA sets a requirement for how big this angle can be. And they typically say that angle can be, this angle here can be no greater, or well, not greater than, it should be less than or equal to about 30 degrees. Now, there are all kinds of formulas I can give you using tans and cosines and tangents and everything like that to figure this out. But we've created an easier way of doing this. Basically, what we say for a ramp is for every 1 inch you go up, the ramp must go out 12 inches. Right? Or what we say simpler is for every 1 inch up, oops, I don't want to do that. For every 1 inch up, it's 1 foot long. So it's kind of like subway. It's a foot long at that point. So let's look at a real world example of this now. So let's say we've got a patient who's got stairs. 1, 2, 3, and there's 4 stairs. So they got to get that one fixed. Most stairs are between 6 and 8 inches tall. Let's just say this patient has 6-inch stairs. So the patient has 1, 2, 3, 4 stairs to enter their home. If they have 4 stairs to enter their home, and each stair is 6 inches, their total amount to go up is 24 inches. 24 inches. So if we plug that into this formula up here, that means for 24 inches up, our ramp is going to have to be 24 feet long. So that means when we design this ramp or give them specs for this ramp, that length there is going to have to be 24 feet. Now, you may remember this from math, talking about that being the hypotenuse of a triangle, and a squared plus b squared equals c squared. You don't have to do that much. This is the formula to use. For every 1 inch you go up, you go out 1 foot. Now you can use this 12 inches. Sometimes the boards may ask you, if you've got 3 inches to go up, how many inches do you have to go out? Well, you're just going to take 3 times 12 and get 36 inches, right? They're not going to make you do this on your boards. We have to do 24 times 12 inches. Don't worry about that. So let's do another problem of this real quick. So let's clear all this. So again, I'm going to put that formula up here in the corner. So for every 1 inch we go up, our ramp has to be 1 foot. No, it's not a foot. Having problems drawing today, folks. Actually, I have problems drawing every day, don't I? 1 foot long, right? So let's say that this time we've got a patient who has 5 stairs to enter, and each stair is, let's just go 8 inches tall. So 5 stairs to enter, but each stair is 8 inches tall. Well, if we know that 8 inches times 5 means we have 40 inches to totally go up. If we have 40 inches to totally go up, how long do we have to make that ramp? Simply just change those inches to feet, and it means that our ramp must be 40 feet. Now, we're going to talk about in rehab that you can't do a 40-foot ramp because that takes a lot of propulsion to get all the way up 40 feet without rolling backwards, right? We got to think about that as well. But for the sakes of this question, that means your ramp needs to be at least 40 feet long. That's it. That's all you have to know for math. You have to be able to go, if I give you a number of stairs and I give you a height of a stair, so I may say the patient has 12 stairs to enter, and each stair is 2 inches high. They're really tiny stairs, but let's just say it is. Well, you know that you've got 24 inches of stairs there. So that means you need 24 feet of ramp. For every 1 inch we go up, we go out 1 foot. That's it. That's why we talk about linear equations in this class is because we will have to do this quite frequently. And you may ask, Mr. McKeever, how often am I going to have to be an architect and design a ramp? Actually, depends. If you work in neurological rehab, it happens quite a bit. Normally, they're going to hire a builder, right? They're going to hire somebody that's professional and knows what the ADA standards are, because there's standards for width of a ramp, there's standards for how the handlebars have to be. But you may eventually get one of those patients that's like, look, I just want to put a quick and dirty ramp on my back door so grandma can get up into the house. What do I have to do? Well, you can use this formula with that patient and say, hey, look, well, how high do you have to go up? Well, I have to go up about 25 inches. Okay, well, then your ramp needs to be at least 25 feet long, right? Well, that doesn't make a lot of sense because sometimes when you think about it, like if you're a business, you may not be able to do that. So a lot of times what you'll see is if businesses have stairs, oh, that's not a very good stair. Businesses have stairs to enter, right? Boom. I'll pretend these are stairs going up into this business, right? It's not feasible for them to make a ramp going out this way. So a lot of times what they'll do is instead make a ramp going off to the side of the stairs to get in, right? But even that has regulations. It still has to be less than 20 or less than 30 degrees out there. It still has to be 1 inch up, 1 foot over length. Now, what if you have a ramp? Let's say that your patient's now got one. So again, I'm going to right up here in the corner for every 1 inch up, 1 foot of length. What if your patient's got a, let's say they have 10 inches to get up into their house. They live in a trailer, which is about a standard height to get into a trailer. So I would say we need about 10 feet of ramp. What if they say, well, my grandma's kind of weak. Can I make that ramp longer? Instead of doing a 10-foot ramp, can I do, I don't know, a 15-foot ramp? Sure. For every foot that you lengthen out, it's going to make it a longer ramp to build. But for every so many feet that you make it out, you're going to decrease that angle of inclination. You're going to actually change this. So here's my 10-foot ramp, right? Here's my 15-foot ramp. If I draw that line, this angle here is steeper than this angle here. They both get to the same point. They both get up to this landing here, right? So this is where grandma's up here. Yay! Right? Found how grandma got up there because grandma's in a wheelchair. So grandma needs to come up in a wheelchair. Now grandma's sitting in a wheelchair, so there we go. Right? So grandma's sitting in a wheelchair. The longer we make that ramp, the easier it's going to be for grandma to go up that ramp. But again, you're hit by constraints sometimes, right? And again, if you make it too long, then grandma may get halfway up this ramp and get tuckered out by herself. And then all of a sudden, back down she goes. We don't want that either. We'll talk about stuff like switchbacks and with the ramps and stuff like that when we get into Rehab 1. All right, let me stop sharing here. All right. So that's it for this portion. We're a little bit ahead, so I didn't want to get into the physical therapy math unless we are together. So our next lesson is going to be the physical therapy math, and that definitely is going to play. It's going to take about 2 classes to go over that, but that's going to talk about, the different applications of math in our physical therapy profession. So that's it for this lesson. I'll be posting a really brief short quiz for this lesson, and then enjoy your anatomy class if you haven't already. I hope to see you soon. I'm waiting on my negative test. Hopefully I should have it today. Yay. And we'll see how it goes. All right. That's it for this class. Thanks for paying attention. Have a good day.